Hey, I'm Byron Johnson with Coordinated Power. Just putting together kind of a brief walkthrough of grounding safety analysis, touch and step voltage, how they happen, what is ground potential rise, and how does all of that work and go together. So I'll walk you through that on these handful of slides to follow. All right, this slide, what is ground potential rise? So ground potential rise happens when fault current goes into the earth through the grid. So you can see here you have fault current coming down maybe a tower, maybe it faults to the steel in the substation. Anytime fault current goes into the earth, there is a ground potential rise. So you can see here it goes into the ground network, and kind of what's happening, let's say the fault happens over here on this leftmost grid. You'll see, well, the picture's drawn the other way, but the same concept. When the current goes into the earth and then disperses in the earth, and then at the return path, the current comes back out, ground potential rises happen in those cases. Again, here it is, slightly more zoomed in on the concept. If you have a current electrode right at the surface and you inject current into earth, the current disperses kind of as it goes throughout these shells. Right, so the first shell, all the current is, let's say we got 10,000 amps of fault current. Goes into this first shell, we got 10,000 amps confined right here. Think of lots of little individual parallel resistors that 10,000 amps is going through. Once it gets through that first shell, it goes to another shell. Then that 10,000 amps is spread out into a larger shell, so more parallel resistors. Then you go through more, in each shell that you go out, you get more parallel resistors, and the current has a little bit less current through each of the parallel resistors as it spreads out and disperses into the earth. And what you end up happening as you get more and more shells, the current starts to get so spread out and have so many different paths through the what we call dirt resistors, basically, that no further shells influence it any further. So take a look at this circuit. If we take two of these dirt injection zones, and we apply a voltage source to it where current will flow. The current will go into the earth over here on this side. It will disperse into the earth, and it'll reach a point out here what the grounding people call remote earth. And remote earth is when the current is so dispersed into the earth that no more shells matter anymore. So at some point, no more of these shells matter anymore, and the current is fully dispersed, and then it's just connected to the earth. And what's interesting is no matter how far apart these two locations are, if they're a few miles down the road or on other sides of the earth, theoretically, all the resistance and happens within the shells that matter. Then we get over here when you have to return back to the source, it has to do it again through a ground connection. Here's the circuit drawn again, slightly different, only so that you can see the voltage loop, right? So you have the whole loop here, and GPR, which stands for ground potential rise, happens across that shell that we're talking, that group of shells where your grid connects to remote earth. And basically what happens is in this circuit, you would have current going through this ground grid into the earth, into remote earth, and that GPR would be across the whole system where it enters into the soil. The top of the grid, or the grid itself, and everything grounded and connected, is the top of this resistor. And then various points on the earth surface and within the earth are at different points of this resistor, all the way down to, if you're sufficiently far away from the grid and the grounded structures, you'll be at remote earth. So at remote earth, the voltage from remote earth, just any dirt out away from where the current's getting injected, will experience the full GPR all the way back to the grid. And if you're standing somewhere on some dirt that's not connected to the grid, you'll be at some indeterminate potential in between the GPR. And that's what we'll talk about more. Here's just another visual depiction of this phenomenon happening. Let's say that we've got, tower fault out here, and it returns to the transformer that's feeding that fault. So the fault current goes into the earth here, and that's the voltage, the ground potential rise, the potential of the dirt around it. Current goes into the earth, and then it comes back here. And then this this height up here would be the voltage of the grid itself, and then as it falls off, that's the voltage of the dirt surrounding the grid out until it reaches back a point that doesn't matter anymore. So it's really that remote Earth is still 0 volts, but Earth, as it gets closer and closer to the energized grid, becomes higher and approaches that ground potential rise voltage. Now, in the case of touch and step potential, what is that? Okay, so we have the full GPR, right? So you can see over here, the grid itself and everything grounded and connected to the grid is the top of that resistor that we had in our earlier circuit. And the dirt that is touching the grid is also at the same full potential of the full GPR. But the dirt starts to fall off in voltage as you move away from the grid. And you can see here, you move away from this conductor and it starts to fall off. And then you move back over here where it's, where you've got conductor again, and it starts to rise back up into it. This picture could be a little bit confusing. You got to disregard this dashed line running here, and these are just, think of these conductors as point conductors, I guess, for the sake of this picture. But the dirt that's touching the conductors is at the same potential, and it drops off as you move away from that and get some distance between the dirt you're standing on and the grid. And what we come up with is touch voltage is the difference between any point of dirt and the grid itself, right? So the dirt here that this person is standing on might be where their feet are, right? So it's at this potential, it's fallen off. But the transformer that he's touching here is grounded and it's at the full potential. So this is the difference. This difference in voltage here is the voltage that this person would be subjected to between their hands and feet. It's the touch voltage. Now over here we've got the step voltage, and it's based off of a 1 meter step, and it's the voltage difference between your 2 feet with the earth that you're standing on, right? So you see 1 foot is on the dirt here, and it's at this potential, and his other foot is at this potential down here. So he'll actually have a current flow that goes up through one leg and out the other leg in the step case. So again, touch is a plot of the potential difference from all locations on the dirt back to the grid. And step is at every piece of dirt you plot the maximum voltage from that point to any point 1 meter away. So what is the touch voltage shock circuit? It's right out of IEEE standard 80. It is an open circuit voltage, and it is based off of the resistance of each foot. So, and you divide it by 2 because your feet are in parallel, and you apply that voltage to the body resistance of the human body, and we'll get to that later, what that's determined to be. But so then you come up with what the tolerable voltage that the person can take for the duration, right? So in grounding studies, we come up with a duration of how long the fault and how long the shock would last based off your body resistance. And given that and this Thevenin resistance that you come up with here and how your feet connect to the earth determines how much, and again, it's open circuit voltage that we evaluate with, but what would be the voltage required to drive that amount of current through the body. Step voltage is similar circuit, again out of IEEE standard 80. Keep going to the next slide. This is also out of IEEE standard 80, and it's just based off what the allowable current is through the human body. And you can see the formula over here as what it's come out to be with the constants. And we typically use the 50 kilogram human value. And basically the allowable current came from a bunch of empirical data from a long time ago and was formulated, and we found the best fit and what we believe right now to be represent what fibrillates human hearts, and that is the allowable current. So just ground grids are designed to based off of the current to not fibrillate your heart. So what's the maximum current that you can be exposed to for a duration without experiencing heart fibrillation? Here it is again, just showing the actual equation and the constants and what's fibrillating and non-fibrillating. But all these values are typically built into software, so it's not something you need to remember. Body current, basically, just to get some idea of how much current your body can handle. Perception, you can perceive about a milliamp, and only about 10 to 20 milliamps before you reach the let go potential, where you can no longer let go. 3 seconds, 0.3 amps for 3 seconds. So human body really, is not overly tolerant on, amp level currents, especially, but it's milliamps that matter. Here's just another one of what IEEE Standard 80 depicts as the electrocution circuit. You're touching something grounded. You're standing on dirt that is not touching the grid. So this dirt, you're right above the grid, so maybe it hasn't fallen off from the GPR too much, and it's not too different in voltage, but there is some voltage difference, and that's the shock circuit. All right, so now that you understand kind of how step and touch potentials arise based off of voltage distribution in the soil, one common way to do it, other than just putting in grounding and grid conductor to equipotentialize the soil, you can put high resistance rock layer on top of it. And most all substations have a rock layer. So this is just a table out of IEEE Standard 80 showing the dry and wet resistivities, which is basically kind of a volumetric representation of resistance that matters on how big the rock is, but you can convert it directly into resistance. But we use these in grounding studies, and we typically use this washed stone here. The number 57 washed stone, you can't see it super good, but it's 8,000 ohm meters wet. That's a good value to use, and we typically use lower than that just to be conservative. And here you can see the kind of how the surface layer works, right? So you've got your actual soil, and maybe at your given substation you've got low resistivity soil on top and high on the bottom, or vice versa. Soil is different at every site. But then you put the very high resistivity surface layer material on top for 3 to 6 inches, and that gives you some extra protection there.